Welcome to Elementary Real Analysis. Today, we are going to explore a fascinating and foundational topic called monotone sequences. Imagine climbing a staircase where you are only allowed to step up or stay on the same step, but you can never step down. Your height above the ground behaves exactly like a monotone sequence. By the end of this video, you will understand exactly what these sequences are, how to test for them, and why they are so incredibly important in mathematics. Now that we have our staircase analogy, let us define this formally. In mathematics, a sequence is simply an ordered list of numbers, and we call each number a term. We say a sequence is monotonically increasing if every term is greater than or equal to the term right before it. In simple words, the list of numbers never goes down. Conversely, a sequence is monotonically decreasing if the numbers never go up. If the numbers strictly go up without even staying the same, we call it strictly increasing. Understanding these definitions allows us to categorize sequences based on their directional trend, which is a powerful tool for figuring out if they eventually settle at a specific value. Before we look at the formulas, let us see this visually. The graph you are looking at captures the essence of monotone sequences. Notice the horizontal axis represents the position in the sequence, and the vertical axis represents the value of the term. The blue dots represent an increasing sequence. See how they steadily climb higher as we move to the right? The red dots show a decreasing sequence, steadily dropping lower. The most important thing to notice here is that neither set of dots ever changes its overall direction. There are no zigzags or sudden reversals. This consistent one-way movement is the defining characteristic of monotonicity. Now that we understand what a monotone sequence looks like, let us write this using mathematical symbols. This gives us a precise rule to test any sequence we encounter. The fundamental definition of an increasing sequence is that the next term must be greater than or equal to the current term. If we rearrange that, we get the subtraction test shown here. We take the next term and subtract the current term. If this difference is always positive or zero, it proves that the sequence is never dropping in value. If the variable representing the difference increases, it means the sequence is growing faster. This subtraction method is one of the most common ways to test a sequence on an exam. Let us apply this subtraction test to a classic problem. We are given a sequence defined by the formula n divided by n plus 1. And we need to prove that it is monotonically increasing. This perfectly demonstrates how to apply our definitions to a real algebraic expression. To use the subtraction method, we first need to find the expression for the very next term. We do this by replacing every n in our formula with n plus 1. As you can see on screen, this gives us n plus 1 divided by n plus 2. Now we are ready to set up our subtraction. Continuing with our proof, we will now set up the actual subtraction test. We want to calculate the difference between the next term and the current term. This will tell us exactly how much the sequence grows from one step to the next. We write out the subtraction using our two fractions. To subtract these two fractions, we need a common denominator, which will be the product of the two bottom parts. We multiply the top and bottom of each fraction appropriately. This crucial step ensures we are comparing apples to apples before we simplify. Now for the final steps of our first example. We need to expand the terms in the numerator. We multiply out the first part to get a quadratic expression and distribute the n into the second part. Notice that the squared terms and the linear terms cancel each other out perfectly. This massive simplification leaves us with a very clean fraction, 1 divided by the product of n plus 2 and n plus 1. Since n represents the position in the sequence, it is always a positive whole number. Therefore, the entire fraction is strictly greater than 0. Because the difference is always positive, we have successfully proven that the sequence is strictly increasing. We just saw the subtraction test. But what if our sequence involves powers or factorials? Subtraction would be too messy. This brings us to the ratio test. If all the numbers in our sequence are strictly positive, we can use division instead of subtraction. We divide the next term by the current term. If the sequence is growing, the top number of this fraction will be larger than the bottom number, making the result greater than or equal to 1. Conversely, if the ratio is less than 1, the sequence is decreasing. This ratio test is incredibly useful for complex sequences where division simplifies things beautifully. Now that we have the ratio test, let us look at a sequence involving exponents. We are given the sequence 1 divided by 2 to the power of n, and we want to prove that it is monotonically decreasing. This type of sequence appears frequently in probability and computer science. Because this sequence involves powers, the ratio method will be much easier to use than the subtraction method. Firstly, we write down the next term by simply adding 1 to the exponent, giving us 1 divided by 2 to the power of n plus 1. We are now ready to divide. Continuing with our second example, we set up our ratio test by dividing the next term by the current term. As you can see, we have a fraction divided by a fraction. Remember that dividing by a fraction is the exact same thing as multiplying by its flipped version, which is called its reciprocal. This simple algebraic trick turns a messy division problem into a straightforward multiplication problem. We now have 1 over 2 to the power of n plus 1 multiplied by 2 to the power of n over 1. Next, we will simplify this using exponent rules. Let us finish this proof. We can simplify our expression using the basic rules of exponents. The term in the denominator, 2 to the power of n plus 1, can be split into two separate bases, 2 to the power of n times 2 to the power of 1. This allows us to clearly see matching terms on the top and the bottom of our fraction. The 2 to the power of n terms cancel each other out completely, removing the variable entirely. We are left with exactly 1/2. Since 1/2 is strictly less than 1, it means every term is exactly half the size of the term before it. Therefore, we have proven that the sequence is strictly decreasing. So, we have proven that sequences can be increasing or decreasing. This brings us to an important question. Why do mathematicians care so much about monotone sequences? The main reason is predictability. In the real world, if you are tracking a declining population of endangered animals or a computer algorithm getting closer to an optimal solution, you want to know where it will eventually end up. Monotone sequences have a magical property. If they are bounded, meaning they have a ceiling they cannot cross or a floor they cannot drop below, they are absolutely guaranteed to settle at a specific limit. This concept is the backbone of calculus and proves that complex models will actually work instead of blowing up to infinity. Let us wrap up what we have learned today. First, a monotone sequence is simply a list of numbers that moves in only one direction, either always going up or always going down. Second, we learned two powerful tools to prove this. The subtraction test, where we show the difference between consecutive terms is positive, and the ratio test, which is perfect for handling exponents. Finally, we discovered that if a monotone sequence is trapped by a boundary, it will always converge to a limit. You have now mastered the foundational tools to predict the long-term behavior of mathematical patterns. Great job, and keep practicing.